Given dy dx equals x minus y, with f of 1 equals 4, approximate f of 2 using Euler's method with two steps of equal length starting at x equals 1? that question mark probably doesn't need to be there. Okay. It makes me think of Ron Burgundy. Okay. So Euler's method idea here is, so we're going to have a graph. The graph looks like this. We're going to have x equals 1. And we're going to have 1, 2, 3, 4. So we're going to have a point like that. And we're going to use the slope to find a line. Hop, hop. And it says, what, 2 steps? 2 steps. So 2 steps, going from 1 to 2, we'll have 1.5. We'll do a step there, and then maybe a step there. So we'll use one step and then another step to approximate each point. Like, what? That sounds super confusing. It's okay, we got this. Not a big deal. So let's see, our first point is 1, 4. I know it's confusing, I just drew an extra arrow on there. Unnecessary confusion. So f of 1 equals 4. F of 1.5 equals f of 1 plus, and I'm going to write this as delta x times dy dx, where delta x is the difference between 1.5 and 1. I could also write this part here as f of 1 plus delta x. So what we're going to have then is 4 plus 1/2 times, and then dy dx is based on our previous data. So we're going to do x minus y. So x is 1 minus 4. So x minus y up there. Oh, lost a parenthesis. So we have 4 plus negative 3/2, which equals 4 minus 1.5, which equals 2.5. So f of 2 equals, f of 1.5. 1.5 equals 2.5. Okay, so to backtrack real quick, idea here, start with a point, draw a line based on the derivative, the slope. A little bit of difference. We know what the change in x is going to be because we know we want to go to 2, and we know we want to take 2 steps. That was given in the problem. If we want to be more accurate, we just take smaller steps. If we took smaller steps, then each individual step would have less error with it. So we're kind of given the change in x. So x will go from 1 to 1.5. The y value then will be the original y value, which was 4, plus the step size, delta x, times the change in y, change in x. And another way you can kind of sort of look at this from an intuitive point of view is this is y, this is delta x, this is dx, kind of sort of the same. So you get y plus kind of sort of a delta y, change in y. And that will then give you your new y value. Okay, we'll keep working through this. So now we know f of 1.5, and I should probably do an approximation thing here. Okay, f of 1.5, okay. So now f of 2 will be f of 1.5, the previous iteration, plus delta x times dy dx. And dy dx will change this a little bit based on the derivative we were given. So f of 1.5, we already approximated that as 2.5 plus 1/2, which is the change. And then dy dx, we have x is 1.5 and y was 2.5. So x minus y would be 1.5 minus 2.5. Yep. Which equals, I can write this in terms of 5/2 plus 1/2 times -1. So we're left with 5/2 minus 1/2, which equals 4/2, which is 2. Let's see if that seems reasonable. It does seem reasonable. Yep, so then our answer for this one will be 2. So, I'm not going to redraw the lines, but that's the idea here. So, backtrack real quickly. To use Euler's method, you have to find out which side your steps are. You determine your delta x. That's either given to you or you can decide it yourself. In this case, it's given to us, so use what they want. We know there's 2 steps. 2 steps between 1 and 2 would be 1.5 and 2. So each step would be 1/2. From there, you take your initial value, which in this case was 4. You added your step size times the change in rise over run, dy dx, if you will. And you do that twice, reiteratively, and you get your final answer of 2. Not too bad. We can do these kind of problems. Go team.